Okay, so, oh, thank you very much.
I'll let you know when it's 5 minutes.
Okay, thanks very much, Shriram, and thank you, Asim and Tirth, and also thank you very much, Paddy, for the opportunity to be here and to celebrate your birthday and all of your achievements. The subject of this talk is quantum fluids in neutron stars, and in particular the puzzle of radio pulsar glitches. And I don't think Paddy has published on this topic, at least ADS says no, but he certainly has published very widely on statistical mechanics and n-body physics and gravitation, and those are of course fundamental to this subject. So I'll start by briefly reminding you what pulsar glitches are and why they're important. Then I'll talk about the long-term statistics of glitches. Turns out that they are non-Gaussian, and that throws up some interesting puzzles. And then finally, some words on gravitational radiation. So just to remind everybody, about 2,800 radio pulsars have been discovered to date, and all of them spin down electromagnetically over millions of years. But there is a small subset, about 5 to 10%, that also undergo discrete, erratic spin-up events called glitches. So this diagram shows schematically the anatomy of a glitch. We have the neutron star spin frequency, which is measured from the pulsations, the radio pulsations, on the vertical axis, time on the horizontal axis. And you can see the star is spinning down, and then suddenly it jumps. Now, the jump is very small, 1 part in 10 to the 10 to 1 part in 10 to the 5 at best. But it occurs very quickly, in less than a minute, and possibly much less than a minute. It hasn't been resolved. Then there's a recovery phase, a sort of exponential over days to weeks, and the rotation of the star asymptotes to a spin-down rate, which may or may not be equal to the spin-down rate before the glitch. Okay, now to try and interpret these glitches theoretically, people work within the context of a multi-component model of the star. So we start with a crust, which is solid. Then in the interior, we have neutrons, which form a condensate, and they behave like a superfluid, so they flow without viscosity. And then there are charged species, protons and electrons, which are locked magnetically to the crust and interact with the condensate through mutual friction. Now we know that a superfluid is quantum mechanically irrotational. So if you force it to rotate, it can only do so by developing quantized vortices, topological defects, each of which contain a quantum of circulation. And it turns out that these vortices find it energetically preferable to get stuck in lattice sites in the nuclear lattice in the crust. This is called pinning. So you have a situation where, as the star is spinning down electromagnetically, the vortices are prevented from moving outwards, which is what they want to do naturally, by this pinning process. And a lift force, the so-called Magnus force, is exerted on the vortices. And when that lift force gets above a threshold, the vortices can't handle it anymore, they all jump out. The angular momentum of the condensate decreases suddenly. The angular momentum of the crust increases by conservation of angular momentum, and that is the glitch that we see. So this is one idea, popular idea for glitches. Okay, now in the last 10 years, many new glitches have been discovered. We have just shy of 500, and the data are now sufficient to be disaggregated so that you can construct probability density functions for individual objects. Now, for a threshold process of the sort I just described, naively you would expect a narrow range of sizes and waiting times because, you know, you wait, build up some stress, then the stress gets released, and then you just go around again. And in fact, we know that about 1 million to 10 to the 12 vortices are involved in every glitch. And so by the central limit theorem, if the unpinning is uncorrelated, you would expect a very narrow range of sizes. and waiting times. But that is not what we see at all. In all except two objects, the waiting times are exponentially distributed. So here we have the cumulative density function for the waiting times for 6 objects with different symbols shown there. The waiting time is scaled in units of the average waiting time, and you can see that they all pretty much lie along this universal exponential curve. The counterexamples are Vela and 0537. These are called quasi-periodic in the literature, but really they're very quasi. Like the waiting times still cover a range of a decade or more, even in those objects. This asterisk here indicates a hybrid object, and I don't want to say any more about it now. Okay, now on the other hand, the sizes are power law distributed. Now I say power law, the data is not fantastic in some cases, but definitely scale invariant, so they can extend over 4 decades in an individual object. Again, the exceptions are these 2 quasi-periodic objects, and the hybrid one is sitting up there. So, power law sizes and exponential waiting times are characteristic of avalanche dynamics, of self-organized critical systems like earthquakes and sand piles, where you have a slow global driver, which in this case is the electromagnetic spin down, which builds up stress, and that stress is then relaxed locally through impulsive stick-slip events. Now, in the case of earthquakes, the stick-slip events are correlated, and that's what leads to the power law statistics. What is the correlation factor in pulsar glitches? Well, to answer this question, we've been doing quantum mechanical simulations of the condensate inside the neutron star. So these, we solved the Gross-Pitevsky equation, which as many of you will know is a nonlinear Schrodinger equation that describes the order parameter for a superfluid. And we solve it in a trap which is decelerating and which contains a grid of pinning sites that co-rotate with the trap, so just like the pulsar. And here you'll see the results. So this is a movie, which I'll show you in a second. You're seeing the density plotted here. High is yellow, low is green. So these green spots correspond to partial exclusion of the superfluid from the vicinity of the pinning sites. And then these blue spots correspond to total exclusion of the superfluid from the core of a vortex. So the blue spots are vortices. We're looking at the condensate from above, so the rotation axis is out of the page. And we're in the instantaneously co-rotating frame. So you won't see the pinning grid rotate, but what you will see as the stresses build up is these vortices move. And when the vortices move, the crust responds, and there's a little black curve here which will come down as time goes by, which shows you the angular velocity of the crust as a function of time. So if we're lucky, you will see some glitches. There we go. Right, so a baby glitch. A bigger one. They're moving.
Disappearing, or?
When they reach the edge, they disappear. I'll talk about that in a second. Okay, and a big glitch to finish up. Okay, so we do get glitches. They occur at random times, as we see in nature. They have a range of sizes, some small, some big. And whenever you do get a glitch, the vortices unpin in groups. There's collective behavior. Now, their motion is 2 types. In one case, they sort of unpin and then dodge past the pinning sites and leave the system, as you were asking, just like a skier. In the second case, they skip over some pinning sites and then repin again. And they do that in such a way as to fill in the gaps of what would otherwise be a sort of quasi-regular vortex lattice. Now, we've identified 2 knock-on mechanisms which produce correlations here and abstracted them from the complicated simulation to look at them under controlled conditions. So the first one is very simple. It's just proximity knock-on. We artificially take this vortex and move it towards this pinned vortex. And when it gets too close, the mutual repulsion kicks this one away. It goes. And as it moves, it emits some sound waves. The second mechanism, knock-on mechanism, is more complicated. It's acoustic, so remote unpinning. We set off a pulse of sound waves here artificially. It washes past this vortex, and this vortex unpins, which it's doing now. Now, as it moves, it emits lovely spiral sound waves. It repins at this pinning site and does a basketball on a hoop thing, emits a strong pulse of sound waves which washes past this vortex, and in a couple of seconds, this vortex will also unpin. There it goes. Okay. So here we've got unpinning at a distance through the propagation of sound waves. Okay, now the Gross-Pitevsky equations simulations are small, maybe 100 vortices at best. But still the statistics are interesting. So the sizes of the events are scale invariant. I won't say power law because we've only got a few events, but they still cover 1.5, 2 decades, even for this small system. The waiting times are very nicely exponential, and the radial displacement of the vortices during a glitch is clustered around the Feynman separation, which is the separation of the vortices in an undisturbed lattice. And these results are pretty much the same whether the pinning potentials are uniform, which is the black columns, or random, which is the green columns. Okay, we can compare with data, very preliminary comparison. At the top, we have the cumulative density function of the waiting times. The simulations are the green triangles. The red is the crab, the actual observations, and the blue are observations of Vela. And then down here, the sizes, again, cumulative distribution. The green triangles are the theory. The red boxes are the crab data, and the blue circles are Vela. And you can see Vela is not a very good fit, which is not surprising. Vela is one of those quasi-periodic objects which behaves a bit differently. I should mention that the Jodrell Bank Group and Cristobal Espinosa have recently claimed to resolve a minimum glitch size in the crab. If that is confirmed, both in that object and in others, then of course it has interesting consequences for a scale invariant process like this. Okay, now just for fun, let me show you another movie. This one is the same style as what we saw before, but we artificially reduced the damping to promote acoustic wave unpinning. And you'll see that, I hope, yep, that there are a couple of differences. Still the behavior is quite similar, but you tend to get larger avalanches that cover more area, and with these very nice worm shapes for the tracks. And also, the recovery after the glitch is more complete than it was in the previous case. And observations do show that some pulsars have a big recovery, and some pulsars have almost no recovery. Okay.
If this is a framework in which it's not rotating, why is it that these glitches are moving in a particular direction?
Well, it's like in a non-inertial frame, you have Coriolis forces and stuff. It's the analog of that. But they're not Coriolis forces, but they're like Coriolis forces. Okay, so obviously to test this observationally, we need even better statistics. And we are, to do that, we're writing, as we speak, a hierarchical n-body code based on the Barnes-Hart algorithm that many of you are familiar with to study larger systems. So here's a preliminary result showing the tracks of a vortex avalanche involving 5,000 vortices out of 9,000 in this system. One important point, this code is not quantum mechanical. So it does not do the acoustic waves, but it does everything else. It does the proximity knock-on, etc. Okay, on to part 2, correlations. So for a threshold process like I've just described, you would naively expect sizes and waiting times to be correlated, because the longer the waiting time, the more stress you build up, and then it gets released. Very important to note that that correlation is not seen in self-organized critical systems like earthquakes, because in those systems, the stress is historical. It's not just since the previous glitch, but also many events in the past. And likewise, we don't see that correlation here. So let me show you the data. Here are the sizes of glitches as a function of the waiting time between glitches, scaled by the spin-down age. You don't need to worry about that. For 5 different objects which have glitched the most, so different colors for each. And you can see that for 4 of them, it's basically a scatter plot, the red ones, the purple ones, etc. But for this blue object, you do actually get a tight correlation with a Pearson coefficient of 0.94. This is the size of a glitch versus the waiting time to the next glitch, the forward waiting time. Okay? Now, you might say, oh, well, maybe these orange ones are also correlated, but they're not really. The Pearson coefficient in that case is 0.6, which is not a lot. Okay, now we can do the same for the backward waiting time. So this is the size of a glitch versus the waiting time since the previous glitch. And here, for all 5 objects, it's a scatter plot. The best one is Vela, which are the green triangles, and it's got a Pearson coefficient of 0.7. So, can we understand this? Well, let's look at this picture at the top left here. What I'm plotting here is the unpinning rate of the vortices, schematically, as a function of the lag between the crust and the superfluid inside the star, the stress. So there's a critical lag where the Magnus force on the vortices is so high that they have to unpin. And the unpinning rate diverges as it approaches that asymptote. So if the system starts in this orange state, it spins down, spins down, spins down, reaches here, then a glitch happens and rolls it back down the hill. Okay, so very important point. The size of a vortex avalanche, both, and this is for self-organized critical systems in general, but also in our simulations, the size of a vortex avalanche is completely independent of the lag. You can have a large lag and get a small avalanche. And that happens all the time. Okay? But there is still a correlation between the size of the glitch and the waiting time. And you can see this in these 2 regimes. Suppose that you have very quick spin down. Okay? So with quick spin down, you're very quickly going to end up against this asymptote. Okay? And so if you then get a large glitch, the time to the next glitch will be quite long. Whereas if you get a small glitch, the time to the next glitch is relatively short, because every time you're coming up against this asymptote. So that's a strong correlation in that regime between size and forward waiting time. I can talk about that later. Nobody knows, but it's the balance between the Magnus force, which is proportional to the circulation quantum and that sort of thing, and the pinning potentials in the nuclear lattice, which nobody knows what they are. Yeah, let's say. Yeah, we don't actually, but one could if one knew more. It is. Yeah, very much so. In the opposite regime, where you have slow spin down, you don't really get to this asymptote. You're down here, and so really there isn't much correlation at all. But there is a weak correlation because it turns out the physics of this process is such that you cannot go negative in the lag. So if you have a short waiting time, you'll only move a little bit to the right, and so then the next glitch can only be relatively small. Whereas if you have a long waiting time, the next glitch can be larger. So there is a weak correlation there. Okay, now how does this compare with the data? Well, here are the Pearson coefficients for those 5 objects we looked at on the previous plots. For the forward waiting times in red, the backward waiting times in blue. High spin down is to the left, low spin down is to the right. And the thing that sticks out is the one that has the forward correlation also happens to have the highest spin down rate. Beyond that, it's not possible to really say very much at all. Okay, so let me conclude with some words about gravitational waves. In glitch studies, the gravitational waves come from the current quadrupole channel, not the mass quadrupole. So this, of course, comes from the momentum flux in the system, or alternatively, the T0I component of the stress energy tensor. So it comes from the velocity field. Now, there are at least 2 ways in which you can get signals. The first is during the rise of a glitch, you get a burst of gravitational waves as vortices move outwards in a non-axis symmetric way. And you can show pretty robustly that if the rise time is less than 10 milliseconds, which is not impossible, that the signal is strong enough for advanced LIGO to see.
This time in what reference frame?
This is again in the co-rotating frame. The second possibility is during the decay phase that we saw on the second slide of the talk. If the glitch produces some kind of non-axis symmetric perturbation in the flow, then you might think, okay, that perturbation will then get erased by things like Ekman pumping and circulation of various kinds over the recovery timescale, which is days to weeks. So in that case, you expect a periodic gravitational wave signal at the spin frequency of the star, which dies out over days to weeks. Now, these have been studied in the literature. I'm not going to talk about them more here. What I want to briefly mention is a third possibility, which is related to this second one. So in the movies that we've seen so far, you will recall that after a glitch, especially after a big glitch, the vortices are not sort of non-axis symmetrically disposed. They're not in a perfect lattice. And that then means, and that sort of non-axis symmetry is going to be erased not only over this recovery time, but potentially over the spin down time of the star, because the way an asymmetry gets erased in one of these systems is to get lots and lots of avalanches and slowly change the configuration. And that happens over the spin down timescale here, which is hundreds, thousands of years. So we have the vestiges of a big glitch, which are going to survive for a long time, and so they will produce a long-lived periodic signal at the spin frequency of the star. So I have some pictures here of asymmetric vestiges of glitches, so-called. Here's a 100-year powder avalanche in Colorado, making a complete mess. Here's a rock fall. And here are the strain patterns in the fault network of an earthquake in Mexico before and after the quake. So, what does this imply for our situation, for vortices and neutron stars? Well, let's begin by assuming that actually there is no non-axis symmetric vestiges from the glitches. We have zero clustering, and the vortices are in a perfectly regular array. Even then, because the vortices are discrete, you have a non-axis symmetry. Small, but it's there. And you can calculate analytically, actually, what the gravitational wave signal you would expect. And it turns out to be small, not surprisingly, 10 to the minus 29 for the fastest spinning millisecond pulsar. But that's not too far away from what a coherent search could achieve with advanced LIGO, which is about 10 to the minus 27. And by the way, this is with zero detuning. So if you tune the interferometer, you might be able to do slightly better. But that's with the rock bottom assumption of zero clustering. Very unlikely that we would have zero clustering when the whole point about the vortex avalanches is that they are driven by knock-on. This is a very correlated process. So the question is, how much clustering do you get from the knock-on? Can you get a factor of 100 to make this detectable? Well, we don't know the answer to that, so we're still working on it. And it turns out it's not an easy problem. Numerically, it's not easy because the systems we can solve numerically are still quite small. You need dynamic range. Analytically, it's not easy because self-organized critical systems are notoriously difficult to analyze, so we're still working on this. But the one point that I would like to make is that if you get a large non-axis symmetry following a big glitch, that will survive, as I said, for roughly a spin down time because you need many small avalanches to undo it. And so we don't actually need to witness the big glitch. It might have happened 100,000 years ago, and its imprint will still be there to some extent. Thank you, and I'm done. So, in summary, glitches have non-Gaussian statistics. The sizes are power law distributed. The waiting times are exponential for most objects. Quantum mechanical simulations of vortex avalanches produce statistics that are consistent with what is observed, although, of course, the number of events, the simulations are fairly small systems. And we have identified for the first time 2 mechanisms within those simulations which can explain correlations, namely proximity knock-on and acoustic knock-on. There is no correlation observed between sizes of glitches and the backward or forward waiting times, except for this object here, which has a correlation, a statistically significant correlation in the forward direction. And again, within the context of that theory, there is a way of perhaps understanding that. And then finally, gravitational waves can be emitted by glitching pulsars in several ways. One way is that you get a burst of waves from the actual glitch event, because the vortices move non-axisymmetrically. And if the event is short enough, like less than 10 milliseconds, LIGO can see that. Another way is that you get a periodic signal at the spin frequency of the star, which lasts, depending on how you look at it, either days to weeks during the recovery phase following a glitch, or if the snow avalanches and everything else I was just talking about is correct, can last for a spin-down timescale. And of course, detection of such a thing would be very important because it would be a direct evidence for nuclear superfluidity in neutron stars, which is, so an idea that's been out there for a long time, but never really proven, and would tell us a lot about the equation of state of bulk nuclear matter. So I'll stop there. Thank you, everybody, very much. And again, Paddy, happy birthday. It's extremely nice to have spent time with you and learned from you. Thank you.
You've not said anything about the coupling between the magnetic lines of force and the vortices, if there is any, and whether in practice the lack of axial symmetry of the magnetic field can do anything to the gravitational field.
Yeah, so this is a very good point. For those who aren't aware, inside a neutron star, if you believe the folklore, which is the same folklore as what I've been talking about, you have a type 2 superconductor. So the magnetic field in the star is concentrated in flux tubes, just like the circulation is concentrated in vortices. And there has been back and forth on this subject for decades now about how strong the coupling is, and there are people in this room who have worked on it, how strong the coupling is between the superfluid vortices and the superconducting magnetic flux tubes. And that ranges everywhere from it's strong to it's not strong. I have a very smart student, Lisa Drummond, who has been doing simulations on this problem recently. And one of the things that she showed is that just like a vortex array, in the picture books you always see these vortices, they're 10 kilometers long and 1 femtometer in diameter, and somehow they're stable. In fact, they're not stable. They make tangles, and you see that in the lab. And likewise, you would expect the magnetic flux tubes to make tangles. And so then that complicates the question of how they interact, right? Because you might be that you have a fairly strong interaction between magnetic flux tubes and vortices if they're straight and crossed, sort of as you're suggesting, because it's not symmetric. But if it's a tangle, maybe they can pass through each other. The picture is a bit unclear. So in the context of what I've presented today, the pinning sites could equally be magnetic flux tubes, and nothing would change from the perspective of this analysis. And the scale of this analysis is such, because of the nature of these self-organized critical systems, it does not matter too much whether, like here, basically we're modeling a two-dimensional slice. And if you had a complicated arrangement of magnetic fields and vortices, you'll have many two-dimensional slices, but the statistics is sort of insensitive to that. I mean, we haven't proven that, but it seems to be that way. So sort of a long way of saying that the magnetic field is very important. It has not been explicitly included here, and we need to think about it. The only other very quick point I'd make about the magnetic field, since it was brought up, is people in the literature, I guess just because it's simpler to say so, have always assumed that the magnetic field inside the neutron star is uniform, or it's a dipole or something. But it could be a complete mess. And in fact, there's a very little read but wonderful paper by Eason in the 1970s where he showed that if you have differential rotation inside the star, then any magnetic field that has some subset of field lines that close inside the star is not consistent with a steady state differential rotation. So you would get some kind of tangling and who knows what that is.
Is there a relationship between the change in magnetic moment or the change in angle of the magnetic field and the glitch?
Hotly debated. So until recently, the data were just not good enough to say one way or the other. Now there seems to be some indications that when you get a glitch, you also get changes to the emission. Now, whether that's a change in that angle or something else is unclear. And just to remind everybody, the radio emission probably comes, we don't know, but probably comes up in from someplace in the magnetosphere, which may be 10, 100 stellar radii from the star. So at that point, really all you are seeing is the dipole moment. And so the only thing you're sensitive to maybe is that change in that angle, you know, if anything, but that would be a fairly small change. It would be great to have something, some emission from closer to the surface of the star that's you know, a good probe, and then you might start to see changes in the other moments as well, which would be definitely informative. Yeah.
For the detection of gravitational waves, how well do we know the waveform of these gravitational waves? Because that goes into the computation of sensitivity, right?
Yeah. Yeah, that's a very good question. So the question was, for the detection of gravitational waves, how do you know the waveform? So I'll answer it two ways. The first is that for the burst signal during the glitch, it turns out actually you can calculate it analytically for any particular sort of set of vortices that have moved. It's not hard. But that, in practice, that's not what they would do. They would just, they've got, as you know, they have many algorithms which make different assumptions. Some model the bursts, some don't model the bursts. But basically, you look for broadband noise over a short period. In practice, that's how they would do that. I have not made that estimate properly. So when I said less than 10 milliseconds, that was just a rough number for that case. For the second case, you actually know that the signal is a sine wave, modulo all the things you don't know. But at least prima facie, signal is a sine wave, and so then you would do all the things that we do in LIGO for continuous wave searches, you would do for that. And there's a bit of a bonus in this case because, for example, when people in the published searches for, say, the crab pulsar, LIGO has done coherent search based on the radio ephemeris. But they need to allow a little range, about 1% on either side of the radio ephemeris, because you don't know that the gravitational wave emitting quadrupole is rotating with the crust of the star, which the electromagnetic emission is tied to, right? It could be something else inside that's a bit different. So that means they have to search templates and then it becomes expensive. In practice, to be safe, you would do the same thing here, but at least theoretically, there's no need to, because these vortices are pinned to the crust by definition, to pinning sites in the crust. So the pattern, the quadrupole rotates actually with the crust in this case, right? On the face of it. But of course, life is complicated, so maybe that's not strictly true.
Okay, let's thank the speaker again.
Thank you.
Our next speaker is Professor Charles Lineweaver. He's going to talk about cosmobiology and the probability of paddy.